Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. We're looking here at inverse hyperbolic definitions and how these definitions are derived. It's not a very lengthy or difficult topic, but this is something you need to know on the off chance that you were given a question, a definite integral question, something which looked like this. This is just but one example only, and we have something here in the denominator which looks like this. We can say from 1 to 2. You know, based on what we've learned recently in the previous two videos, the inverse hyperbolics with regards to their integrals and the derivatives, you know this right here is an easy antiderivative of something which looks like this inverse hyperbolic cosine, but again from 2 to 1. Now you actually need to know what this really literally means in terms of its definition so that you could plug it in. If hypothetically a question was such, a certain question over here with regards to an integral, and the answer of that integral, you could even say, let's just say sine hx for simplicity's sake, and you know the antiderivative of sine hx is cosine hx, and then you have 2 to 1. Here you know how to do it because we know the definition of this. This is e to the x plus e to the minus x over 2. You would then plug in these 2's and 1's and you could take this forward to completion. Our problem is, what does this mean? Or what does inverse hyperbolic sine mean? What does inverse hyperbolic tangent mean? How do you handle these three specific inverse hyperbolic antiderivative functions with regards to definite integration? And that's something you should know, and that's something which this video will address. Let's look at this busy slide over here. We're looking at the definition of hyperbolic sine, cosine, tangent, which you've seen multiple times, and you know this right here is easy. The definition of these hyperbolics gives you terminology or equations which include exponential functions. When you look at their inverse hyperbolic counterparts, inverse hyperbolic sine, you're looking at natural log parentheses x plus root x squared plus 1. Inverse hyperbolic cosine, you're looking at natural log x plus root x squared minus 1. And then here, the inverse hyperbolic tangent, 1 over 2 natural log 1 plus x over 1 minus x. These are the three definitions you should know. But look, a very interesting trend comes out. These regular functions, the non-inverses, have definitions which involve exponential functions. These inverse hyperbolics have definitions which involve natural logs, and you know this right here has an excellent relationship of f of x and inverse of f of x. Just like these are inverses of one another, their definitions or their equations are inverses of one another. These involve natural logs, these involve exponentials. But an interesting thing, additional fact you should know is when you're looking at this definition over here applies for any value. X is an element of all real numbers, because there's no way when you're looking at that natural log, technically there's no way that you can zero out the denominator or bring in an issue such that you'll have a negative square root. But when you're looking here at this, there's a potential for having a negative root. You cannot zero out a denominator, but you can end up having negative root leading to an imaginary solution which you do not want. In this instance, this equation holds for those values where x is greater than or equal to 1, because then you'll avoid having an imaginary solution develop. In this instance, when you're looking over here, your domain is rather restricted to avoid having a 0 in the denominator, to avoid having a natural log of a 0 or a natural log of a minus 1 or a minus number, because you cannot do a natural log of 0, you cannot do a natural log of negative numbers. Here your domain is rather restricted such that x is less than 1 but greater than minus 1. So something you should be familiar with. What we look at next in the remainder of this video is how can these definitions be derived, and you'll find it to be a very interesting procedure. And you will see why the previous two videos before this were very much important into this development of these definitions. We'll end the video then with a definite integral question which will involve this, something I alluded to at the very beginning of this video. Let's look at the development of this inverse hyperbolic sine definition. The procedure starts with you realizing that the derivative of the inverse hyperbolic sine x is equal to the simple one that you know, 1 over root 1 plus x squared. The procedure next evolves into you taking the integration of this, the integral of that. And this is just but one way I'm showing you, but this is an interesting way because it depends on the derivative and the integration aspects to come up with those definitions, and along with that, the understanding of the trigonometric substitution technique. You do the integral of that and you can do dx over root 1 plus x squared. You've seen something like this in the previous video. You have a trigonometric expression hidden here of the form a squared plus x squared, which tells you A here is equal to 1, x is equal to tan theta, and dx is equal to secant squared theta d theta. You plug all of this into this expression, you get secant squared theta d theta. Here in the denominator you'll have 1 plus tan squared theta, which easily boils down to secant squared theta, the root of which is just secant theta. You do secant squared theta d theta divided by this secant theta, and you end up getting secant theta just as your numerator, which gives you the antiderivative natural log secant theta plus tan theta. We don't have to write plus c because we have to evolve this into the definition, and it's not hard. You look again right here at x is equal to tan theta, and theta here is equal to arc tan x, or x over 1. You develop a triangle. Here's your theta, here's your x over 1 for the tangent function, and then this must be x squared plus 1. When you solve for this expression here with regards to this triangle and for the theta, you'll easily get to that definition, and you do natural log secant of this arctan x is going to give you root x squared plus 1 plus tan of theta, which is tan of arctan x over 1, and that's going to give you your x. And this right here will give you the definition of the inverse hyperbolic sine, utilizing derivative, the integral, and then trigonometric substitution technique to carry it through to a good definition. And that right there is it. It's a similar procedure for these other two, and it's not hard. The inverse hyperbolic cosine is interesting. You do the derivative of this inverse hyperbolic cosine function, and you get 1 over root x squared minus 1, and you know that as the derivative of this. You do the integral of that, you dx over root x squared minus 1, and you have a trigonometric expression hidden here of the form x squared minus a squared. A is equal to 1, x is equal to secant theta, dx is equal to secant theta tan theta d theta. These are those trigonometric substitution techniques that you know of. You put everything here into this. You have secant theta tan theta d theta, and over here you'll have x squared minus 1, which is secant squared theta minus 1. All of this boils down to a tan squared theta. The root of that is tan theta. That denominator tan theta will cancel out with this numerator tan theta, and you'll just get secant theta d theta, which is going exactly in the same direction as the previous one. The antiderivative of secant theta is natural log secant theta plus tan theta. The difference arises now as you examine this expression over here, x is equal to secant theta, and you solve for theta. Theta here is equal to arc secant x over 1, and you develop a triangle based on this, and this is where the difference will arise. Here's your theta, secant x over 1 is this, and then this must be x squared minus 1. You plug everything with regards to this theta into this triangle, and that'll give you your definition. What's secant of theta? You get secant of arc secant x, and that gives you x over 1. I'm not writing over 1. Then you're looking at tan of this theta, tan of arc secant x over 1, that's root x squared minus 1 over 1, and this right here gives you the definition that you want for your inverse hyperbolic cosine, as it is right over there. The procedure for deriving this is the most difficult, but it's not hard in the sense that you're having a difficult derivative and integration process. The difficulty arises when you have your actual outcome and you have to do algebraic manipulation to get to that. So you can see that, and I'll put that out. Start with here the derivative of this inverse hyperbolic tangent. You know that to be 1 over 1 minus x squared. You have to do the integral of this, and you'll set it out as dx over 1 minus x squared. But this is of the form a squared minus x squared. Here a is equal to 1, x is equal to sine theta, dx is equal to cosine theta d theta. These trigonometric substitution techniques coming here. You have cosine theta d theta. Here you'll have 1 minus sine squared theta. This right here is equivalent to cosine squared theta. So you're looking at cosine theta d theta divided by cosine squared theta, which is no different than you saying d theta or cosine theta, which is no different than just secant theta d theta. Antiderivative all along for secant theta to be natural log secant theta plus tan theta. We won't write the plus c. Here again everything comes down to this triangle. You're looking at everything here with regards to this. If x is equal to sine theta, theta is equal to arc sine x, or x over 1, and you develop everything based on that x over 1 and 1 minus x squared. When you put everything into this definition here, secant of arc sine x is going to be 1 over root 1 minus x squared. We have a natural log here. and then we have a plus right here. Tan of this arc sine x is going to be x over root 1 minus x squared. We can combine all of this to 1 plus x over root 1 minus x squared. So this is where we are, and this right here is equivalent to this right here, and I just have to show you that. I'll make some space and we'll manipulate this algebraically to bring it to that. The way you can convert this into this is by looking here at this expression. Let's put this. We have 1 plus x, and then we open this up. This is the same thing as saying 1 minus x times root 1 plus x. Look at it. Root 1 minus x times root 1 plus x is equal to the entire 1 minus x squared within a single radical, and that's a property of radicals. What you can do over here is take this numerator expression and this denominator expression and simplify them. This root 1 plus x goes in 1 plus x whole to the 1 times. It goes 1 plus x root times. Think about it. This right is 1 plus x to the power of 1. This is 1 plus x to the power of 1 over 2. And you can bring this 1 plus x radical in the numerator, and you have 1 minus x here in the denominator. What you can do is use the properties of radicals and put everything like this into a single radical, and you have this. What you can do now is rewrite everything, and we can even eliminate the absolute value parentheses, because we already have our domain defined such that we won't need to use the absolute value over here. We have 1 plus x over 1 minus x, but here to the power of 1 over 2. You can bring this right out here, and you get 1 over 2 natural log 1 plus x divided by 1 minus x, and that gives you the definition of this inverse hyperbolic tangent, which is what we wanted all along. More work in the algebraic manipulation than the previous derivation part. So we end this video with a single definite integral question which drives home the point why you needed to know the definitions of the inverse hyperbolic sine, inverse hyperbolic cosine, and the inverse hyperbolic tangent. When you're looking at this, you know clearly there's a good antiderivative out there for something which looks like this, and the antiderivative happens to be inverse hyperbolic cosine. You have this upper limit 2 and the lower limit 1. Now you know how you can do this because you know the definition of this function. This function has a definition natural log x plus root x squared minus 1. You're looking at everything from upper limit 2 to 1, which is not hard. You're going to put the 2's in, then you're going to put the 1's in and do the difference of the 2, but you'll do them separately. You'll do natural log 2 plus root 2 squares of 4, 4 minus 1 is a 3. Minus, this is now the lower limit coming into play. You have 1 plus 1 square minus 1. When you do this, you'll have a 1 plus 0. You'll end up having a natural log of just a 1. This zeroes out. Essentially, you're just left with natural log of 2 plus root 3. You can bring a scientific calculator, compute this, and do the natural log, which will give you your answer of 1.31695, and that answer would be right. And that would represent the area below the curve for a function which has this interval and this demonstration to this. And that right there is inverse hyperbolics in a nutshell. Thank you for watching. Have a nice day.